Good afternoon and welcome to the CEC live lecture session. Dear friends, today we are taking a series that is Mathematical Methods for Economics, and in this series today's topic is logic. To discuss this topic within studios with us we have Dr. Neeti Bhutani. Dr. Bhutani is a senior lecturer in Department of Economics in Hindu College. Dear friends, for today's ongoing lecture, if you have any queries or questions, you can call us on our toll-free number, that is 1800111043 in the last 10 minutes of this lecture. So let's start with this today's lecture and let's welcome ma'am to the studios. Welcome ma'am to the studios.
Thank you, Seema. Hi there everyone. This is our fifth lecture in the series Mathematical Methods for Economics. The topic for today's lecture, as Seema just pointed out, is logic, and it also happens to be one of my favorite topics as far as teaching is concerned. Having some knowledge of logic is always a good idea for any student or professional, and you will see that once you get the hang of things, once you get the hang of the terms or concepts that we're going to introduce in today's lecture, once those concepts come into your awareness, you can start using these concepts while writing your term papers or any research paper, or for that matter, you could also use these concepts in your daily usage of language. The particular terms that I would like you to get acquainted with by the end of this discussion is deductive versus inductive reasoning, the terms converse and contrapositive. I would also like you to be familiar with what are necessary and what are sufficient conditions, as well as the use of the words if, only if, and if and only if. Finally, we will end our discussion, if time permits, with a discussion of mathematical proofs, where we will distinguish between a direct proof and indirect proof, and we'll also talk about proof by contradiction. But before I get into the details of logic, the formal details, let me talk a little bit about why it's important to study logic, and let me motivate this discussion with the help of a story which is popularly known as Russell's paradox, after Bertrand Russell, who was a philosopher and mathematician. It's also known as a Barber paradox. So the idea behind the story is that very often we make statements which on the face of it may appear okay, fine, but actually they are logically impossible. So the story goes like this. There is a village in which there is only one barber, and all the men in the village, if they have to go for a shave, they go to this local barber. They get their shave done through this local barber. And there is a sign outside the barber's shop that says, if you look at this visual, I shave all those and only those who don't shave themselves. So please, I would request that this visual be shown. The barber sign says, the sign outside the barber's shop says, I shave all those and only those who don't shave themselves. The question now is, who shaves the barber? Now, there are two possibilities that emerge here. There are two possible scenarios. One is that the barber shaves himself. Now, the point here is, if we assume that the barber shaves himself, well, he mustn't, because the statement above, if you look at where my cursor is pointing, the statement above says that the barber shaves only those who don't shave themselves. So herein we have a contradiction, because we assume that the barber shaves himself, but the statement says that the barber should not shave himself. Similarly, if we look at the second possible scenario, that is, the barber does not shave himself. So if we assume that the barber does not shave himself, again we have a contradiction, because our statement says that the barber shaves all those and only those who don't shave themselves. So the idea behind the story is supposed to drive home two main points. One is that statements that may appear to be logically plausible are actually logically impossible. So, we have to be careful about how we phrase our sentences, and secondly, this story drives home the point that you also must have a good knowledge of logic. So, let's get into the discussion of logical reasoning, and we'll start our discussion by first defining a proposition, because it is propositions that we will be working with throughout this lecture. A proposition, if you look at this visual, the slide, a proposition is an assertion, it is a statement that is either true or false or open. So, let's look at some examples. If we look at examples of true propositions, so if I say the Taj Mahal is located in the Indian city of Agra, this is an example of a true proposition. Similarly, the identity x plus y the whole square is identically equal to x square plus 2xy plus y square. This identity is also an example of a true proposition. Similarly, if we look at the statement, the last statement in the slide, it says NAFTA, which is a North American Free Trade Agreement. This is a trade agreement signed by Canada, Mexico and the United States, which again is an example of a true statement, a true proposition. A false proposition would be, for example, all cats are white. Clearly, all cats are not white, and this is a false proposition. Similarly, if I say the government of India announced demonetization of rupees 100 notes in November 2016, this is also a false proposition because the demonetization announcement was for 500 rupees and 1000 rupee notes. Then finally, let's talk about open propositions. So, if we look at the statement x greater than y, this is an open proposition in the sense that we cannot decide whether it's true or false, and we can decide if it's true or false only if we assign certain values to x and y. So, for example, if x is 5 and y is let's say 2, then clearly this would be a true proposition. But if it's the other way around, let's suppose x is 2 and y is 5, then this would become a false proposition. So, in this sense, this is in general, it's an open proposition because we will decide whether it's true or false only on the basis of the values that we have for x and y. Similarly, the equation that says x square minus 9 is equal to 0. Again, this would be true or false depending on the values that we assign, the value or the values that we assign to x. So, for example, if x is 2, then clearly 4 minus 9 can't be 0. But if x is 3, then this equation will be satisfied. So, depending on the value of x, this proposition will be true or false. Now, as far as logical reasoning is concerned, logical reasoning can be classified as either deductive reasoning or inductive reasoning. Deductive reasoning is reasoning based on consistent rules of logic. So, to see this, let's suppose I have two propositions P and Q. And if, let's say, whenever P is true, then Q is also necessarily true, which is to say that whenever P is true, this leads us to say that Q is also necessarily true. This is then written as, if you see where my cursor is pointing, if P then Q, and this is to be read as if proposition P is true, then proposition Q is also true. So, the idea here is that you start with a proposition, or you could start with a set of propositions which, if true, can be used to logically deduce other propositions. And that is why we say this is deductive reasoning, because we start with a certain set of assumptions which, if true, lead us to some other set of propositions, and these propositions are deduced from the assumptions. Now, statement of the form if P then Q can be mathematically expressed as P implies Q, which is where my cursor is pointing, you can see here. And this can also be read as Q, the proposition Q is a consequence of proposition P. Now, while I won't get into the details of mathematical proofs here, let me mention it in passing that this statement of the form P implies Q is a mathematical representation of what is known as a direct proof in mathematics. And we'll come back to this in a bit in some time when we discuss mathematical proofs. Okay, so this is as far as the basics of deductive reasoning are concerned. Let us now talk about inductive reasoning. So in inductive reasoning, we start with some data, and on the basis of that data, we look for a pattern. We look for a pattern in the data, and on the basis of that pattern, we generalize and draw our conclusion or conclusions. In fact, inductive reasoning is of fundamental importance in the experimental sciences, in the empirical sciences. It is an important tool which is used for empirical work. But please note here that inductive reasoning is not recognized as a form of proof in mathematics. And to see this, to appreciate this, let me explain this with the help of an example. So these days there's a lot of talk about fuel prices. Elections are around the corner, and a hot topic of discussion is prices of petrol and diesel. So let us suppose I obtain data on fuel prices, quarterly data on fuel prices for the last 5 years, and I observe that for every quarter the fuel prices have been increasing. The price of fuel has been increasing in every quarter for the last 5 years. So on the basis of this, can I say that in the next quarter also the price of fuel will increase further? Now, all of you will agree with me that if fuel prices have been increasing for the last 5 years in every quarter, this sort of gives us an indication of things to come. But can we use this as a proof to say that fuel price will be higher even in the next quarter? So in that sense, because we can't use this as a proof, inductive reasoning is not recognized as a form of proof in mathematics, but deductive reasoning is. And please also note here that when I talk of inductive reasoning, while inductive reasoning is not used as a form of proof, this is not true of mathematical induction. So this is just an aside. Mathematical induction is a valid form of proof. This is a mathematical version of induction. It is a valid form of proof, and in fact it is used to verify formulas that involve natural numbers n. Here if we look at the way mathematical induction, the principle of mathematical induction is used, actually, I don't know if you know this is actually based on deductive reasoning. And you will just see in a bit why it is deductive reasoning. So even though we use the word induction in mathematical induction, it is actually using deductive reasoning. So to see this, let us see how mathematical induction works. So here we are looking at, our question is a given mathematical statement or formula true for all natural numbers n? Now, if you're familiar with mathematical induction from school, you would know that we do two checks for mathematical induction. First, we check that the statement is true for n equal to 1. And second, we check that the statement being true for n equal to k also implies that the statement is true for n equal to k plus 1. So this sort of sets up a cycle so that every time the statement is true for n equal to k, it is also true for n equal to k plus 1. And if we if our procedure passes both these checks for n equal to 1 and the statement being true for k, implying that the statement is true for k n equal to k plus 1, then we say that the statement is true for all natural numbers n. So note here that the syntax of the statement that I have on the slide, I am starting by saying if a of 1 is true, suppose that is the same as if. So, if a of 1 is true, the statement is true for n equal to 1, and if a of k is true, then a of k plus 1 is true, then a of n is true for all natural numbers n. So, if you look at the syntax of this statement, the structure of this statement, the semantics, this structure is actually what we use in deductive reasoning, because deductive reasoning is the statement that we use in deductive reasoning is if P then Q, and this is exactly the same structure here. If these two assumptions are true, one for n equal to 1 and n equal to k, implying n equal to k plus 1, then the statement is true. So, mathematical induction is based on deductive reasoning and it is a valid form of proof. So, this was just as an aside. Let me come back to our discussion of deductive reasoning. So, let us suppose our statement that involves deductive reasoning is given by if P then Q. And as I've just mentioned this, I mentioned this a little while ago, that this is written as P implies Q. Now, let us look at some examples of implications that are of this P implies Q format. Let us suppose proposition P is X is a healthy person and proposition Q is X is breathing. So, in this example, we have that if X is a healthy person, then X is breathing, and that is logical, because if X is a healthy person, then he is certainly alive and therefore he is breathing. But note here that the implication will not go the other way around. We can't say that if X is breathing, then X is a healthy person, because you may be breathing, you may be alive, but it's not necessary that you are healthy. So, here the implication goes from the left hand side proposition to the right. Similarly, if X, let's say, is a positive number, then this implies that the square of X is also a positive number. And finally, we have this example that if xy is equal to 0, the product of two numbers is equal to 0, then X is equal to 0 or Y is equal to 0. And please note here that when I say X is equal to 0 or Y is equal to 0, this actually represents the union of the two sets. So, this is to be read as X is equal to 0 or Y is equal to 0 or both. So, if I look at my left hand side statement proposition, that is saying xy is equal to 0, and if I solve it, it will be 0 either when X is 0 or Y is 0 or both are 0, which is what the right hand side proposition says. So, there will be an implication arrow that goes from left to right in this case, and in fact you will see that you can also draw an implication arrow from the right hand side proposition in this part to the left, because if X is 0 or Y is 0 or both, then certainly xy is also necessarily equal to 0. Right. Now, if we look at deductive reasoning in a set theoretic framework, then the statement if P then Q can be interpreted as follows. Let's suppose I have a member of the set, let's suppose a proposition P is represented by a set P, and if I have a member X which belongs to P, and this implies that X also necessarily belongs to Q, then in terms of a Venn diagram, this is represented as P implies Q, or P is a subset of Q. And you can see here, if my cursor is pointing here where let's suppose this element is lying in P, so automatically whenever P is true, Q is also going to be true here. So, if so this is where my cursor is pointing. So, if X belongs to P, X automatically belongs to Q. Now, some people often say when I ask how would you show the statement if P then Q through a Venn diagram, some people come up with this kind of a Venn diagram where Q is a subset of P, but note here that this would be incorrect because let's suppose the star, this red star which you see in the set, bigger set P, where my cursor is pointing, let's suppose that red star is located here, then you can see that if this red star belongs to P, it's not belonging to Q. So clearly it will not fall in line with the statement if P then Q, because here we are saying that if the member of the set P, which is X, belongs to P, it is also necessarily belonging to Q. So this is incorrect. Now, what we are saying here is that whenever I say P implies Q, that is the same thing that is equivalent to saying that P is a subset of Q. And in fact, this is something that you should take note of, because once we start doing examples and problems relating to deductive reasoning, this actually gives us a very neat way of handling the problems, because all you have to do is look for the smaller set of possibilities, and the implication arrow will always go from the smaller set to the larger set. Right. Let us now define the converse of the statement P implies Q. The converse of the statement P implies Q is Q implies P. And here the line of reasoning goes from Q to P. But note here that the converse need not always be true. So for example, when I say X is a healthy person and that implies that X is breathing, this if I look at the converse, that would read like X is breathing, but that does not necessarily mean that X is a healthy person. So in this case, the converse is not true. Similarly, if I say X is positive, implies X squared is also positive, which is true. The converse will not be true here, because the converse says that X square is greater than 0 implies X is greater than 0. Clearly that can't be the case, because if X squared is greater than 0, X could either be a positive number or a negative number, and on the right hand side we just have a positive number. So the implication can't go from left to right. Right. But if the converse is true, so if the statement P implies Q is true and its converse Q implies P is also true, then we say that P and Q are equivalent. Proposition P is equivalent to proposition Q, or in terms of the terminology that we use in logic, we say P if and only if Q. And please note here that when I say P if and only if Q, to represent that P and Q are equivalent, this is also written as P I double F Q. This is to be read as, whenever you see I double F, this is to be read as P if and only if Q. So examples of equivalent statements would be as follows. So let's suppose my proposition P is xy equal to 0, if you look at this slide, and proposition Q is x is equal to 0 or y is equal to 0 or both, which is that meaning is already in here, it's inherent in this statement. Then these two propositions, as I explained a little while ago, these two propositions are equivalent. Similarly, the proposition x being a positive number is equivalent to saying that x cube is also positive, because if x is positive, then clearly x cube, this implies that x cube will necessarily be positive, and if I have the proposition x cube is positive, that also necessarily implies that x is a positive number. Before I start talking about problems, before I move on to discuss some examples, let me establish one more result, which is that whenever I say P implies Q, that is equivalent to not Q implies not P. Now this statement, if you see where my cursor is pointing, not Q implies not P is also known as a contrapositive of the statement P implies Q. and this not Q implies not P forms the basis of what is known as an indirect proof in mathematics, or proof by contrapositive. So let's prove this. Whenever P implies Q, we have established that P is a subset of Q, which you can see in the Venn diagram. Now, if P is a subset of Q, you can see from the Venn diagram that not Q is going to be a subset of not P, because not Q is the area in blue and not P is the area in orange. I think it's looking like a little mango yellow. So the area in this mango yellow color and the blue color, that will be not P, right? That's P complement. So you can see here that not Q is a subset of not P, and this is equivalent to saying that not Q implies not P, because whenever we say P implies Q, P is a subset of Q. So similarly, whenever I say not Q is not implies not P, that's the same thing as saying not Q is a subset of not P. So if I establish that not Q is a subset of not P, that is equivalent to saying that not Q implies not P. Right, so we have reached the end of the first part of our discussion today, and we'll continue after a short break.
Thank you, ma'am. Dear friends, here we come to the half of this lecture, and so we'll stay here for a short break. But before going to break, let me remind you that if you have any questions and queries regarding this ongoing lecture, you can call us on our toll-free number, and that is 1800-110-430. So see you after a really short break. Welcome back, friends. Today we are dealing with the topic logic in our series Mathematical Methods for Economics. So let's start with the rest of the lecture. I would request ma'am to please continue with the lecture. Ma'am, please continue.
Thank you, Seema. Welcome back, viewers. So before the break, we had established the result that P implies Q is equivalent to not Q implies not P. Let us look at it. Let us look at an example for this. So suppose my statement is if given the demand curve, there is a rightward shift in the supply curve of good X, then the equilibrium price of good X falls. In fact, I can break this up into two propositions. Proposition P could be there is a rightward shift in the supply curve of good X given the demand curve, and proposition Q could be the equilibrium price of good X falls. So here you can see that P implies Q, and this is equivalent to saying that not Q implies not P, so that if the equilibrium price of good X does not fall, then given the demand curve, there is no rightward shift in the supply curve of good X. So we can use either one of these statements. Right, so we will now do some exercises to see if how well you've understood the implications. And here in this exercise, you're supposed to fill in the blanks either with the forward implication arrow or with the backward implication arrow. And if both the implications work, then you will enter the equivalence arrow in the box. So the first example is where proposition P or the left side proposition is X is a square, and the right side proposition is X is a rectangle. And here we can think of a square as a kind of rectangle. So if we can read things like this: if X is a square, then that necessarily means that X is a rectangle. The implication will go from left to right. And please remember the trick that I had talked about in one of the earlier slides, that the implication will always go from the smaller set to the larger set if we can talk in terms of sets, or we just solve the question in a language framework. So if P is true, then we ask ourselves if Q is also true. Okay, now the second statement says on the left hand side, X is equal to minus 8 to the power 1/3, or the cube root of minus 8. And the right hand side proposition is X is equal to minus 2. Here we can see that both propositions are equivalent, because if I solve the left hand side proposition, that is X is equal to the cube root of minus 8, which implies that X is equal to minus 2. So here we will enter the equivalence arrow. Okay, now the third statement is as follows. The left hand side proposition says that X square is greater than 4, and the right side proposition says that X is greater than 2. Okay, so let's examine the left side proposition a little bit, because we'll have to solve this inequality. I think you all know by now that if X square is greater than 4, it implies that X is greater than 2, or X is less than minus 2. And clearly this is the bigger set, and if you compare it with X strictly greater than 2, here the implication arrow will go from the right side proposition to the left side proposition. There you are. Okay, so the fourth statement now, the left hand side statement is X is a healthy person, and the right side statement is X is breathing. And as I just mentioned a little while ago, if X is healthy, if we have a person who's healthy, he's clearly going to be breathing, but we can't say that this is true if we go the other way around, because the person may be breathing but he need not be healthy. So in this case, the implication will go from left to right, and we'll enter the forward implication in the box. Right. If our left side proposition is now A equal to B for two real numbers A and B, and the right side proposition is A square equal to B square. Let's see what this means. The right side proposition A square equal to B square implies that A is either equal to B or it is equal to minus B. So in this case, we'll have the case that the left hand side proposition will imply that the right side is true, but not the other way around, because if we look at the right side proposition, that is A equal to B or A equal to minus B, but that can't imply that the left side will be true. So here our implication arrow will go from left to right. In question 6, we have X square equal to 9 as a left side proposition, which means that X is equal to plus minus 3 if we solve this equation. And the right side proposition is X is equal to square root of 9, which is to say X is equal to 3. So here, if we again look for the smaller set of possibilities, that's on the right hand side, and the implication arrow will go from right to left, because x equal to 3 implies that x is equal to plus minus 3, but not the other way around. In the next case, we have x equal to 5 as the left side proposition, and the right side proposition is 2x minus 1 is equal to 9. Now, the right side proposition, if we solve this equation, we get x is equal to 5. So, that is the same expression that we have on the left side, which is to say that the two propositions are equivalent. And finally, if we look at the statement, x is equal to root 4, and we have to connect it to the proposition x is equal to 2. This again would have an equivalence between the two propositions, because x is equal to root 4 is the same thing as saying that x is equal to 2. Now, this is an example from Sitzeder and Hammond, the textbook that we use for the mathematical methods for economics. Let's see how you will enter the implication arrows in this set of examples. So, the first statement is where the left side proposition is x is equal to 2 and y is equal to 5. And the right side proposition is x plus y is equal to 7. Now, you can see here that the left side proposition x is equal to 2 and y equal to 5, that certainly implies that x plus y is equal to 7, because if I substitute x equal to 2 and y equal to 5, I get 7. But the reverse implication will not hold, because x and y could be numbers like 1 and 6 respectively. You still get a sum of 7. So, if x is equal to 2 and y is equal to 5, this implies that x plus y is equal to 7, but not the other way around. Now, in the second case, we have the left side proposition as x minus 1 times x minus 2 times x minus 3 is equal to 0, and the right side proposition is x is equal to 1. Here you can clearly see that if the right side proposition is true, if x is equal to 1, then clearly the left side proposition will necessarily be true. But if we solve for the left side proposition, that gives us x could be 1 or 2 or 3, and we take the union of the set here. So, that will not imply that x is equal to 1. So, here the implication arrow will go from right to left. X equal to 1 implies that the equation on the left side is true, but the equation on the left side could be true even when x is equal to 2, for example. So, in that sense, we'll have the implication arrow going from right to left. Okay. So, now let's look at this equation. X square plus y square is equal to 0, and we have to connect it with x is equal to 0 or y equal to 0. The left side proposition is saying x square plus y square is equal to 0, and if you solve this equation, you see that this equation is satisfied only when x and y are both 0. So, you see that here this can't imply that x is equal to 0 or y equal to 0, because if only x is 0 or only y is 0, then this equation can't be satisfied. However, the reverse implication will work. Oh, I'm sorry, this is, I think I made a mistake, yes, yeah. So, if x and y are both 0, then this will imply x is equal to 0 or y equal to 0, yes, because we're taking the union here. So, the right side proposition is suggesting that x is equal to 0 or y is equal to 0 or both. So, the left side proposition will certainly imply that the right side is true, but the right to left implication will not follow, because if only x is 0 or only y is 0, then we can't have x square plus y square equal to 0. So, you can see here that this can be a little tricky. Right. So, let's look at the fourth statement. We have x equal to 0 and y equal to 0 as a left side proposition, and on the right we have x square plus y square equal to 0, and clearly these two would be equivalent, because if x and y are both 0, and that is also the solution we get on the right hand side, then the two propositions have to be equivalent. Okay, if xy is equal to xz, Do we say that y is equal to z? Does this necessarily imply that y is equal to z? No, because for example x could be 0, and in that case y need not be equal to z. But the right to left implication will work, because if y is equal to z, then this necessarily implies that x times y is equal to x times z. Finally, if we look at the left side proposition in statement 6, it says x is greater than y square, and that clearly implies that x is positive, but x positive need not imply that x is greater than that number, particular number y square. So here the implication arrow goes from left to right. The next thing that we are going to discuss in this segment is the concept of necessary and sufficient conditions. So suppose you look at the statement P implies Q, then here the idea is that if P is true, then Q, proposition Q, is necessarily true. So we say here that proposition Q is a necessary condition for proposition P to be true, because whenever P is true, Q is necessarily true. And in the language of logic, this is written as Q if P. The way to read this is you start by seeing where the word if is written. So you start reading from there, if P, then Q. So Q is a necessary condition for P, would be written as Q if P. And at the same time, we can also write here that P is a sufficient condition for Q, because whenever P is true, that is sufficient to say that Q will also be true. In fact, if you remember, in a set theoretic framework, we had expressed this as P is a subset of Q. So that whenever P is true, that is sufficient to say that Q will also be true. And the language that we use for sufficient condition is P only if Q. So whenever P is a sufficient condition for Q, you will write P only if Q. And if we have that P and Q are equivalent propositions, then we say that P is both a necessary and a sufficient condition for Q. That is P if and only if Q, or as I mentioned a couple of slides before, P IFF if and only if Q. Okay, so let's look at some examples here. Here I'm going to give you two propositions in every case, and you have to establish whether the line of reasoning runs from A to B or B to A, or both propositions are equivalent. And in particular, you have to establish whether A is a necessary condition or a sufficient condition, or both necessary and sufficient for B to be true. Basically, you have to remember that if the implication goes from left to right, from A to B, then A will be a sufficient condition. If B implies A, then A would be a necessary condition. And if A is equivalent to B, it will be both necessary and sufficient. So the first example says, proposition A is two numbers x and y are even. And proposition B says the sum of x and y is even. Now here you can clearly see that A, the proposition A, implies that proposition B is going to be true. So whenever we have two numbers x and y which are even, the sum of those two numbers will also be even. However, the reverse implication will not hold, because you may have two numbers like 3 and 7 which are odd, but the sum is also even here. The sum is even here. So in this case, your set B, proposition B, represents a larger set of possibilities. So A implies B, and therefore we say that A is a sufficient condition for B. Okay. The second example, where proposition A is Ali's vehicle has 4 wheels, and proposition B is Ali's vehicle is a car. And you can sense the reasoning, the line of reasoning here. Here, if Ali's vehicle is a car, then it necessarily has 4 wheels. But you can't have things the other way around, where if the vehicle has 4 wheels, it necessarily has to be a car. So here we have that B implies A, which is to say A is a necessary condition for B to be true. The right side proposition is always a necessary condition. Okay, the third example says x is equal to minus 64 to the power 1/3, where x is a real number, and proposition B is x is equal to minus 4. And here it's very obvious that both the statements, both the propositions are equivalent, and therefore A is both a necessary and a sufficient condition for B. Right. If proposition A is a number n is odd and proposition B is a number n is a prime number strictly greater than 2, here we'll have that B implies A, because you could also have a number like let's say 9. So for example, it is an odd number, but it is not a prime number. So we can't have A implies B, but definitely if we have a prime number which is strictly greater than 2, then we'll say that the number is odd. And in this case, therefore, because B implies A is a necessary condition for B. Next example gives you the proposition A as x, y and z are 3 different points on a plane, and proposition B is x, y and z are 3 different points on a circle. And here circle would just represent one set of possibilities. So in this case, if B is true, then A is also true, but not the other way around, because a plane could take any other shape as well. And therefore A here is a necessary condition for B to be true. Okay. Now, in the same way that we entered, we decided whether a proposition is necessary or sufficient for the other proposition to be true. We can also work our way around this, and I can ask you something like, fill in the blanks with either if or only if, and if the statements are equivalent, if and only if. And remember that if P is equivalent to Q, which is to say P is a necessary and sufficient condition for Q, this is the same thing as saying P if and only if Q. And here, when P is a necessary condition for Q, remember for necessary we write if, so we'll write P if Q, and if P is a sufficient condition for Q, we'll write P only if Q. Right, so if we look at this example, in the first one we have the left side proposition as x equal to root 4 and square root of 4, and the right side proposition is x is equal to 2. So here you can see that these two would be equivalent, so we'll write if and only if. In the second case, where x square is greater than 4 is a left side proposition, this is to imply that x is greater than 2 or x is less than minus 2. That would represent a larger set of possibilities. So that would, the line of reasoning would go from right to left here, which is to say that we will have if in the answer, because if x is greater than 2, then x square is greater than 4, but not the other way around. Now, if x square is less than 9, which is our third example here, then that is to say x lies between minus 3 and 3, and the right side proposition is x is less than 3. That is to say that the line of reasoning would go from left to right. So x lying between minus 3 and 3 is sufficient to say that x is less than 3. So we will write only if. And in number 4 we have x times x squared plus 1 is equal to 0. So here if we solve this equation, we'll get this, that this implies x is equal to 0, and these two statements, the one on the right and the one on the left, will now become equivalent. So we will enter if and only if. In the next statement we have x times x plus 3 is less than 0 on the left hand side, and x is greater than minus 3 on the right hand side. So if we solve the left hand side inequality, you can solve it, and you'll see that you'll get x lying between minus 3 and 0, and in this case that's a smaller set as compared to x greater than minus 3. So this answer here, the implication would go from the left to the right, so we will enter only if. In the next example, because if x is an integer, x belongs to R, but not the other way around. Again, x being an integer is a sufficient condition to say that x belongs to R. So we will enter only if. The seventh example here says that 3x plus 8 is greater than or equal to 17, which is to say x is greater than or equal to 3, and that implies that x is that is actually a smaller set as compared to x greater than or equal to 1. So the left hand side condition is sufficient to say that x is greater than or equal to 1, which is to say that we will enter only if. And finally, if we have let's say C, which belongs to an interval set D, let's suppose C is a maximum point for a function f, that is our left side proposition. The right side proposition is f of x is less than or equal to f of c. The value of the function at any x is less than or equal to the value of the function at c. Then these two statements will be equivalent, because c could also lie in an interval or c could be a point, but as long as f of x is less than or equal to f of c, c is a maximum point in that set D, and therefore here we will enter if and only if in our blank. Right, in the last part of the lecture today, we will talk a little bit about mathematical proofs. There are three kinds of proofs. A direct proof, as I mentioned earlier, is the one that goes from P to Q. So you start with P and you successively work forward to prove that Q is also true. An indirect proof takes the form not Q implies not P, that is the proof by contrapositive. And finally, we have a proof by contradiction, where the idea is that if a statement, we'll assume that it is let's say false, but if by assuming that it is false we arrive at a contradiction, then that statement has to be true. So our statement here is P implies Q. So if we assume that this statement is not true, that is the same thing as saying not P implies Q. And this is logically equivalent to saying, if you look at the slide here, that P and not Q are true. So what we will do is we'll start by assuming that proposition P and not Q are true. Propositions P and not Q are true. And if in this we arrive at some logical contradiction, we will say that P has to imply Q. Let's look at an example here. So suppose this the question asks you to use the three different methods of proof to prove that minus x square plus 5x minus 4 greater than 0 implies that x is a positive number. Now in a direct proof, you start with the left hand side proposition, let's call that proposition P, and you'll go on to prove the right side proposition, which is proposition Q. Now if you notice here, the left side proposition minus x square plus 5x minus 4 greater than 0, that if you factorize, that implies that x lies between 1 and 4. So clearly that implies x has to be positive. This would be an example of a direct proof. An indirect proof is a proof by contrapositive. So we'll assume that Q is not true and we'll prove that not Q implies not P. Now not Q here, if you follow my cursor, is x less than or equal to 0, because the complement of x greater than 0 is x less than or equal to 0. But you can see here that if x is less than or equal to 0, then 5x would also become negative, and the entire expression on the left hand side of proposition P minus x square plus 5x minus 4 will also become non-positive. So in this case, we have that not Q implies not P. Minus x square plus 5x minus 4 less than or equal to 0 is not P. So this is the case of an indirect proof. And finally, we can show a proof by contradiction also, where if you remember what I said, we'll suppose that the statement is not true, which is to say that there exists an x such that both P and not Q are true. So P is minus x square plus 5x minus 4 and greater than 0, and not Q is x less than or equal to 0. So if this statement is true, then we'll see what happens. Now you can see that clearly x less than or equal to 0 is logically inconsistent, as we just showed in the indirect proof. X non-positive is logically inconsistent with minus x square plus 5x minus 4 greater than 0. So clearly there is a contradiction within this statement, and therefore we cannot have this to be true, and therefore P must be consistent with Q and not it's not that P is going to be consistent with not Q. So I'll just quickly do one more example, which I also assign to my students for as homework. If let's suppose I ask you to prove that if x plus y is greater than 7, then x is greater than 2 or y is greater than 5. Here we can use an indirect proof, which is not Q implies not P. Let us suppose our proposition x plus y greater than 7 is proposition A, and x greater than 2 or y greater than 5 is proposition B. So not B would imply would be the same thing as saying x is less than or equal to 2 and y is less than or equal to 5, and you can see here that if I add the two inequalities, I get x plus y is less than or equal to 7, which is clearly the case of not A. So we have proven that not P implies not A, which is logically equivalent to A implies B. So with this, we reach the end of our discussion of the topic logic. I was a little skeptical about whether or not I would be able to finish this topic today, but I have managed to complete at least whatever I do with my students in class. In fact, a little bit more. And so this is what we do for today's lecture. In the next lecture, I will be talking about functions. I'll introduce the idea of a function, and we'll also do some coordinate geometry. So until then, goodbye, take care, and thanks for watching.
Thank you, ma'am. Friends, the logical effects of this today's topic logic must have added to your knowledge of economics. We at CEC are always ready with such informational and educative lectures. So stay tuned with us. Thanks for watching.